I would like to introduce our speaker, Yasin Yazıcıoğlu. This is going to be the first out of several mini talks during the summer. We'll try to keep you a little bit more engaged and more with positive energy, because there is a lot of negative stuff happening around us. So, how everybody's doing?
Trying to stay well and healthy and optimistic.
Yeah, let's try to be. I can tell you one of the things, and I will send my normal email, but I have been distracted the last few weeks with what is happening a few blocks from my house. The demand for the master's program the last few weeks is increasing by a couple of applicants per day. So we have 24 committed students. The majority of them are either US citizens or international students in the US. As soon as SAR is back, we're going to accept another 6. The majority of them are from local companies. So there is a lot of, I think this program may exceed our expectations. So given the circumstances, but the positive thing, there are a lot of people from local industry, especially the last 4 weeks. So without further ado, let me. So the talk. So Yasin is a research assistant professor in electrical engineering. The title is Distributed Learning for Optimal Planning in Persistent and Cooperative Missions. He did his postdoc at MIT, and his PhD is from Georgia Tech. And welcome.
Okay, thank you, Nikos, for the nice introduction. And thanks to everyone who is joining the webinar today. I hope everybody is staying safe and healthy during these rather unusual times. So let me share my screen. So it says host disabled, attend the screen sharing.
I can take care of this. Just give me 1 second.
Okay.
All right, I made you a co-host. Can you share your screen now?
I think it works, yeah.
Perfect.
Now everybody sees my screen, I guess.
Yep, you're good.
Okay. So today I'll be talking about distributed learning for optimal planning and long horizon cooperative missions. And the talk will basically have 3 main parts. First, I will start with some introduction and motivation. Then in the main body of the talk, I will talk about this distributed planning problem and how we can use tools from game theory and learning in games to solve these type of cooperative planning problems. And finally, I will conclude with some ongoing work and future directions. So the main focus of this talk will be on multi-agent systems. And multi-agent systems basically appear almost everywhere, ranging from infrastructure networks to multi-robot, sensor network platforms, or Internet of Things. And the standard setup that we have is there's a large number of decision makers in the system, and they're usually operating in a distributed manner based on some partial information about the overall system. So not everybody sees exactly what everybody else is doing, but they have access to some limited information and act on that. And usually we have some global objectives, such as the overall efficiency, robustness, or stability, or adaptability of these type of systems. So an important feature in multi-agent systems is coordination. So everything about their performance really depends on having a proper coordination among these systems, which are usually very large scale. So of course, coordination can be formulated in different ways. Here's just one way of doing it and the way that I'll be using in this talk. So I'll be considering agents, each of which has a set of feasible actions. And these actions can be anything in general. It could be the position of a robot, it could be the trajectory over some horizon, energy consumption, routes taking, or which customer or task to serve. And usually the coordination can be captured by some global function, phi, that depends on the actions of everybody. So in the title, I say persistent mission. That means basically we are considering a long horizon mission, right? At every step or episode, if you want, there's some score that we obtain based on the choices at that episode, and these things keep evolving over time. So of course, the challenges here is that, as I was mentioning in the beginning, each agent chooses its own action independently of the others. And sometimes this is because of scalability, like we don't want to be telling everybody what they should be doing if there are so many of them. And sometimes it's because of privacy. For instance, if I have humans in the system, I cannot really tell them exactly what to do, and they have some private information that we don't have access to. Usually there's limited communication, so as I was saying, not everybody sees what everybody else is doing, and there might be some additional constraints like the dynamics of these physical systems, maybe something about energy consumption or the overall safety. And this phi basically can be changing significantly over time. It might have a very complex structure. It doesn't have to be, for instance, some submodular function, or if you were in a continuous domain, it may not be really a convex function. So I will talk about a particular coordination problem in this talk, which I'll be referring as a cooperative planning problem. So this problem is a distributed high-level planning problem over a discrete environment. So in this environment, we have some obstacles, and there are some stations in the environment where our robots are deployed to. And the system evolves over episodes, and each episode has a time horizon, say capital T. And we have some incoming task requests, and we will have some distributed algorithm that I'll be explaining in this talk. And then the output will be basically the trajectories for that episode. And the goal is this global score is going to be the sum of value of service provided to each of these tasks. And I will be explaining this as well. So some applications could be, for instance, this could be a warehouse. I might have actually robots that can do some box handling in the environment, or it could be an aerial monitoring scenario where the task might be, at this location, I want this many drones doing some sort of monitoring task. So due to energy limitations, we think of robots that need to start and end each episode at their assigned stations, and they can move to any of the adjacent cells in one time step. And since this is a high-level planning on a coarse representation, we don't worry about collusion. So each of these cells are actually sufficiently large spaces, so that can accommodate any number of robots. Tasks, on the other hand, will be defined by 4 things. So they will have a location in this environment, and then they will have some arrival and departure times. So they should be served over this time window, and there will be a value function. And this value function basically maps the number of robots serving that location over the corresponding time window to some value. And what I mean by robots serving that location is that any robot RJ is serving this location at this time instant if it spends one time step there at that location. Okay, so here's one example. Suppose that we have one robot at station 3 and one robot at station 2, and the episode length is 5 time steps. So there's one task at this location marked with this green star, active during this time window, And suppose that what the robots are doing is just go there, serve that location as long as they can, and then come back before they run out of energy. So then the number of robots serving this location can be represented as a vector over this time window. And this is the active time window of the task. So this is really what matters in terms of this counter. So one example, for instance, there might be a few heavy boxes there, which requires 2 robots to lift. And the task may be, okay, you're successfully completing it if there was a time instant where the number of robots there was at least 2. Or it could be that there are several light boxes. In that case, I don't have to have 2 robots at the same time there, but I sum up the robots over the time horizon and they should be doing something, which represents the overall robot time step workload, let's say, of moving these light boxes. Of course, these can be much more generic than that. So here are some related problems. The problem is kind of related to multiple problems that are widely studied in the literature, ranging from scheduling, resource allocation, path planning, and vehicle routing. And these references by no means are exhaustive. I mean, some of these problems, they have books dedicated to them. So the closest one would be actually a vehicle routing problem. But the problem we are posing here kind of generalizes it in the sense that the task specifications can be arbitrarily complex. So I just showed a couple of examples for the value functions. But in general, we can accommodate any function in there. Task might be requiring multiple robots for multiple time steps. You know, they can be preemptible or not. They can be binary tasks, as I showed. So if you're successful, you get a reward. If not, you don't. Or there could be just intermediate values. And there might actually be tasks that require some complex preconditions. Things like, first, I should have at least 3 robots for a couple of time steps because they are going to be moving some heavy obstacle, but then the rest of the mission can be completed by a single or multiple robots. Things like that can all be encoded in the value functions. Okay, so that kind of concludes the introductory part. And in the main body, I'll be talking about how we can use ideas from game theory and game theoretic learning to solve these type of planning problems. So once again, this is just an illustration of the problem that we have. We have tasks arriving over time. We want to generate the trajectories. We need a distributed, we want a distributed algorithm in here. And I'll be talking about how we can use game theory for that. And one might say, why game theory? Well, there are multiple reasons. One is basically game theory is a natural framework to study systems involving multiple decision makers. There are many tools and algorithms with formal guarantees, like we can ensure certain performance. And another one is it can actually accommodate various forms of information and decision models, which later can be extended to accommodate like humans in the system, for instance, decision makers who have private information. Okay, so game theory is a theoretical framework for studying interactions among strategic agents. And this can be used to model various type of problems that we face in our daily lives or problems with multiple vehicles, multiple robots, or other machines. And there are lots of structures in game theory. The games can be simultaneous, like in rock, paper, scissors, or it can be sequential, like in chess. It can be zero-sum, somebody wins, somebody loses, or it could be something else where we don't necessarily have a loser or winner, but some other special structure in their utilities. So it can be used both for modeling, so we might be actually observing a system and trying to explain why is this happening, what are they trying to optimize, and why are they behaving like this? Or we could be using it as a design tool, where we are trying to design the utilities or pricing mechanisms or allocation rules to achieve some desired behavior by this multi-agent system. So in this talk, I'll be talking about a design framework, and we can categorize these things, these type of multi-agent systems, into 2 groups. So one is systems where we also have uncontrollable agents, or we could simply say humans as well. So there are components that we cannot manipulate directly, and we cannot force them to reveal whatever information that they have. In that case, the area of game theory would be mechanism design. So it will be more about pricing and resource allocation type of ideas. Or we might have all controllable agents, like a multi-robot system, where you can access the information, current energy level, or whatever you need from these systems, and you can tell them to do an algorithm that we design, follow an algorithm that we design. So this talk will be more about on this side, although I'll be mentioning some things towards the end about mechanism as well. So in the next few slides, I just mentioned some game theory basics. This is kind of explaining the most standard setup in here. A game basically has a set of players. So these are our decision makers. Then there's an action space. So each AI is the actions available to agent I. And then utility functions, each of which maps the joint actions to some reward for the agent. So for instance, for two-player games, it's usually represented as a table here. So we have player 1, player 2, 3 actions for player 1, 2 actions for player 2. Player 1 in this combination gets the first value. Second value is the utility of player 2. An important equilibrium concept in games is Nash equilibrium. And that is basically any configuration where none of the agents would want to deviate, because given the actions of others, there's really no other action that would yield a better payoff for that agent. For instance, here, agent 1 is getting 4, switching to this, any of these actions would reduce its utility, and same for agent 2 as well. It's receiving a 5, and switching to right would just reduce its utility. Now, I'll be talking about games with a special structure, and they're called potential games. And a potential game is basically a game where we can assign a global function to all of these combinations, such that for any unilateral deviation, so from here, anything in this column or in this row, the resulting change in the utility of the corresponding agent will be equal to the resulting change in this global function. So here, if agent 2 switches to this action, its utility goes down from 4 to 3. Same change is represented in the global function as well. Similar things can be shown for all other switching, all other possible switching in the system as well. So what potential games do is they actually establish an alignment between some global functions and utilities of the individual agents. So if this phi, for instance, if we can design a game such that this phi, this global function, is actually representing what we want from the system. So that's what we mean as coordination in the system, right? Then each agent optimizing its own utility might actually be helping with the global performance as well. So this can be done by learning algorithms. In learning algorithms, we play the same game over and over. So this is the initial stage, next stage, and this will be continuing. At each stage, one of the agents might decide to change its action. So this green circle here is marking the current state of the game. So suppose that initially we started here, and agent 1, for instance, decides to change. It can, for instance, follow best response strategy and move to this cell, and this will continue. So how do we design these type of games? So one way to design these type of games is to use this idea of marginal contribution utility. So we have this global function on our mind. We have scores assigned to all these configurations. Then the utility, if we assign the utility of each agent as its marginal contribution to this score, then we can obtain a potential game where the resulting utilities will satisfy this property. Okay, so in this slide, I'm just explaining how we can design a game like that with that special structure for this planning problem. In this problem, our players are well defined. They would be these robots, and their actions would be the trajectories over the horizon of the episode. And then the utility, this marginal contribution utility idea means that the score that we can assign to each of them can be total value from the tasks with I in the system, agent I in the system, minus the total value that we will be gathering without I in the system. So again, just one example to explain this idea better. So this is the same example that I was mentioning in the beginning. Suppose that we have two agents going here, serving this location and coming back. So these are the counter values over the horizon of the task. And suppose that we have a scenario where there are a few heavy boxes. So it's looking at the maximum value of this counter. It says it should be 2. In that case, as you can see, the task is completed. And if we remove any of the agents, this value would be dropping down to 1. So removing any of the agents means that this task would be failing. So we would get a 0. In this case, both agents should be receiving a utility of 3. Alternatively, let's say we actually have a few light boxes there, and all we needed was just one robot to be present there for one time step, right? In this case, again, the task is completed, but note that none of the robots is actually critical. So that none of them have a really major marginal contribution to the system. Remove any of them, you still have the task completed. So even though the task is completed, under this marginal contribution idea, both robots would receive a utility of 0. Okay, so once we have the game designed, then the next step is actually finding a learning algorithm so that they can iteratively update their choices to hopefully converge to a useful configuration. So one standard algorithm that can be used is best response strategy. So at every iteration, we have a random agent updating its choice. And suppose that it's agent 1. If it looks at these values and say, hey, if agent 2 is going to play left, what is my best choice? Well, it would be choosing this D, down action. And then at the next time step, again, we can pick randomly another agent, and that agent can do follow a similar procedure. We can do those type of best response strategies, which are kind of like gradient descent in optimization, greedy ideas. Or we could have some stochasticity in these decisions to avoid some undesired configurations in the system as well. So one stochastic idea like that is this log linear learning, where the agent actually assigns probabilities to all these possible choices, but the ones that give better utility get a significantly higher probability. So for instance, again, this best response transition would now happen with this probability, which gets arbitrarily close to 1 as we increase beta. And of course, there are many variants or different type of algorithms that follow similar type of ideas. In general, it's either a greedy choice or some stochastic choice. So both of these algorithms come with some performance guarantees if you pair them with a potential gain. And for best response, we have the following guarantee. If you run this game over a large number of time steps, eventually we are guaranteed that with probability 1, the agents would arrive at the Nash equilibrium and stay there. In this game, for instance, there are 2 Nash equilibria, one here, one here. So start anywhere, you'll end up with at one of those. If we follow the log linear learning idea, then what we have is a Markov chain over this action space. And as we increase the noise or beta here, actually reduce the noise, then all this mess of the limiting distribution will be focusing on the configuration that gives the maximum value for this global score, shown in red. So there are 2 Nash equilibria. If you're using log linear learning, by increasing this parameter beta, we can ensure that in the long run, almost always the system will be at this configuration. So then the choice between these type of strategies really depend on the structure of the game. Does the game have very bad equilibria? If all the equilibria are good, we can use a greedy strategy, because anywhere we will converging to will be acceptable. But if the game can actually have some very bad equilibria, then we might be more inclined to choose something stochastic. So, and the planning game that I presented actually happens to have arbitrarily bad equilibrium in general, unless we have a special structure on the value functions. So this is just a simple illustration of this. In this example, suppose that we have two stations, one robot here, and there are these other locations. So suppose that at each location we have a task, and one is basically involving, so these two are involving light boxes that one of the robots can complete by itself. And the task in the middle requires both of the robots to go there, right? Suppose that this value 2 is actually much larger than value 1 and value 3. So we can show that this game would have two Nash equilibria, one where each of them goes to one of the tasks and completes it by itself, and another one where they actually collaborate and complete this task. The reason that this is a Nash equilibrium in this case is because if any of the agents, while in this configuration, decide to go to this other task in between, the task is not completed. So this requires two robots. This robot would not be having any value and will not be receiving any utility, as opposed to receiving a utility of V3 in the first case. So in general, the ratio of the best to the worst is V2 divided by V1 plus V3, which can be arbitrarily large. Of course, this is not the only case where we can have such poor equilibrium. This is just one example showing that in general, unless we impose some structure in the task specifications, best response strategies may not be a good fit for this problem. Okay, so with that, we actually have the outline of the game theoretic design that we can use to solve this problem. We can map this problem to a potential game and then ask each agent to follow a noisy strategy to optimize their choice trajectory for this episode. Say run it for a sufficient amount of time, then stop. And whatever the current trajectory is at that point, we can just dispatch the robots for that episode complete, come back, again, another set of tasks will be arriving, and do this again. One important thing here is that the agents would only need some local information to follow this algorithm. What that means is basically to compute its own utilities, an agent at this station, and if the tasks are here and the time horizon is not very long enough, it would never meet with an agent from this station. So when it's computing its trajectory, it only needs to coordinate with the other agent from this station. And also it doesn't need to know the values or anything about the specifications of these tasks either. So this is just showing what the algorithm would be doing, what the agents would be doing in their updates. And again, the result is kind of something about the limiting distribution of the smart function. So of course, in reality, we would want this equilibrium behavior to emerge as quickly as possible, because there's some amount of time that we would have between two episodes. We cannot wait arbitrarily long for this to happen. So a couple of things can be done to improve its speed. For instance, instead of picking just only one agent at each time step, we could actually have agents who do not interact, who do not influence each other's utility updates simultaneously, which would give some improvement. But the most important part that defines the scalability of this approach would actually be the size of the action sets, because they determine the speed of convergence for this overall process, and also they would define the computation load at each iteration, because we are assigning probabilities to every action in the action set. Now, if we just take this initial design, where we have the action sets defined as the feasible trajectories, we have a problem, because the number of feasible trajectories actually grow exponentially with the episode length. So then what we did here was, can we actually reduce the number of actions, but without losing any performance, global performance, meaning that the remaining set of actions in everybody's action set should still allow us to achieve the best possible configuration. So this is kind of showing the optimization problem here, but the idea is basically finding the smallest set of actions such that the robots are serving only locations during their time windows, and we can remove trajectories as long as there's another superior alternative in the remaining set, meaning that we can remove a trajectory EI if any time instant during the time window this trajectory was serving a task, we have another trajectory in there that's giving us the same servers to the same task. And we can actually show that, we have shown that after we do this reduction, the best possible configuration you would have by taking all the feasible trajectories into account. And after this filtering, they have the same performance. We don't have any performance loss by this filtering. So one may wonder, that's great, but what is the improvement? Well, the improvement is actually very significant. So here is one example. So suppose that we have an episode length of 6 time steps, and tasks are at these marked locations, and we are looking at a robot from the station. The number of trajectories that leave the station and come back within 6 steps is actually 11,000 trajectories. But after we do this filtering and remove all the inferior trajectories, so to speak, we end up with just 9 trajectories for the robots here. Of course, that translates to a significant improvement in the computation time and scalability of the algorithm. So on this slide, I'm just showing some simulation results. And in this simulation, we again have this environment. We have an episode length of 8 time steps. We have 7 tasks, and the task specifications are given in this table. So each task, locations are shown in this figure. There's an arrival time, departure time, there's a value, and there's a number of robots requirement. There are 2 types of tasks, as you can see here. The greens are the type of tasks where we actually sum up the counter values, and if they meet some threshold, the task is completed. The blues, they require this many robots to be there for one time. So 2 robots should coordinate and be there exactly at the same time and stay there for one time step. So you have 10 robots, 4 robots assigned to this station, 4 assigned to this station, 2 robots here. And here you can see the number of trajectories. For a longer episode horizon, this number actually increases much more significantly. And after the significant reduction, we actually ran the simulation on a computer, where the computer was doing the following. Pick one agent randomly, follow this idea, emulating this distributed algorithm, basically. As you can see, so for this case, 30 is the maximum value. Within 300 iterations, the problem actually is solved in the sense that the agents are agreeing on this particular configuration. So it roughly, on this computer, it roughly takes about 10 seconds to generate the action sets for this problem, and then about 15 seconds to run this many iterations, which means that we can actually solve these problems of this size in real time. So this next slide, I will be showing you some experiment results. So these experiments were performed in an indoor facility where we have a Vicon motion capture system. In this video, there will be 3 drones. So these are crazy fly drones, small drones that we can fly indoors. And there's a list of 8 tasks here with locations marked as shown here. So these are the task specifications. We won't be having all of the 8 tasks appearing at every episode. So this video will be showing the behavior of the robots over multiple episodes. And the idea is some subset of these will be arriving, and those will be highlighted during each episode. The other numbers will just disappear, and we'll see that the robots go out and follow certain trajectories to complete the tasks. And the video, by the way, is 4 times faster than the actual. So the first round, we have these 4 tasks. So the robots spread out. Now this one is serving task 2, this one is serving task 1, and they together serve this task 1, and they just go back to their stations. New tasks, they saw some trajectories, 2 robots serving this particular task, task 7, Then they moved to this location where we needed 2 robots to be present for one time step. They completed and come back. Another set of tasks for another episode. Again, they're completing and going back. So in all of these episodes, the combinations were, all the tasks were completed. Of course, in general, you could have more tasks and the agents might actually be missing some of them. So the final one. Okay, so that kind of concludes the main body of my presentation, and I will now continue with some ongoing work and future directions of this research. So one of the interesting future extensions of these type of ideas is, I think, this idea of having some on-demand robotic system that actually serves the request by users. For instance, we might have an aerial imaging system, like we have a set of drones deployed throughout a region, and a lot of users, be that farmers or people trying to monitor their construction areas, maybe emergency responders, infrastructure monitoring, they request some imaging task. And basically, the way this differs is now these task specifications are coming from strategic people who would want to benefit from this system as much as possible. So of course, everybody would want the best quality of service right away at the lowest possible cost. So if you don't have some proper incentives in the system and allocation strategies, then we may not be able to achieve a good social welfare from the system, because we wouldn't have much flexibility, time flexibility from the incoming requests. And for instance, somebody might say, I want a very high resolution image of my farm, images taken from multiple locations simultaneously. So you end up with a task specification that requires a large number of robots, which could have served other people. So this then, this game theoretic thinking then also helps us, because the related idea would be then a mechanism design problem. I mean, one way to approach this would be through mechanism design. So another thing is, so throughout the talk I was mentioning a homogeneous system. So there were identical robots. We just thought about how many of robots we had at certain locations. But of course, in many real life applications, we might actually have heterogeneous systems. And heterogeneity might be in their physical capabilities, like sensing, actuation, locomotion modalities, as in the examples here, illustrated here. But it can also be in behavior. Like agents, even if they have identical capabilities, might actually be following different decision and control algorithms. So the extension of the approach that I presented to accommodate physical heterogeneity is almost, would be straightforward. You could just define a different transition system or a dynamical model for each type of robots. So maybe one of these obstacles do not apply to certain type because it's an obstacle on the ground, and I have drones flying over them, right? Or vice versa. It's a no-fly zone, but my ground vehicles can actually go through. And we can define different counters. And the task specifications might then include things like, first, I should have 3 robots of this type doing something, which is a precondition for the other type robots to come in. Maybe they have to be there at the same time. So you can actually accommodate much more complex tasks by doing that. The behavioral heterogeneity part is, I think, also very interesting and perhaps not well explored so far, because most of the standard algorithms that we would have in learning, optimization, or control, it would be in the multi-agent systems. It would be if all agents follow this policy, if everybody follows this particular learning algorithm, something happens. But there are questions of both design and robustness. So, which means that if we design a different system where some of the agents behave differently, could we significantly improve the overall performance? Or could the performance significantly degrade just because some of the robots are actually following a different set of set of rules. So one problem of interest that kind of relates to this heterogeneity is if we have these type of systems, suppose that some of the robots are following an algorithm that we have designed, but some of the other robots are actually being controlled by a human or multiple humans. How much the performance, overall performance will change? And as a preliminary investigation of this idea, I had an undergraduate student working on a Europe project where we designed a computer game that involves a cooperative mission. It's not this trajectory planning mission that I presented, because we wanted a more intuitive game for people to play, but still an interesting cooperative problem. And the problem that we chose was actually coverage control. So, and the problem is as follows. You have a set of robots and there's an environment. There are some items, valuable items in the environment. What you want robots to do is to spread out and protect them as good as possible, or maximize the value of protected items. And in this game, what we did was we gave them the screen. So if any player that's playing this game would see, for instance, this is their agent marked, and there's some region showing what are the items that can be protecting, and there's a color. So darker shade means somebody else is also protecting those cells, and light green means that only this agent is protecting. So we give them this information and expect them to act based on this information. So there's this limited visibility or a fog around them, emulating the fact that in most cases we would have some local information available. So the way to, I mean, we can use similar game theoretic ideas to solve this problem as well. In this case, basically the actions would be the locations of the robots, and we can define the utilities as the value of cells only covered by that specific robot, because that's the marginal contribution of the robot to the overall protection. So we designed this game for 3 players, and each player controls one robot, and players do not know how many other humans are in the game. Sometimes there are two others are just bots following our algorithm. Sometimes they're all different human beings. And there's no explicit communications between anyone. So you see the screen, you make your move. Do you want to stay or do you want to go to one of these adjacent cells? It's a turn-based game. We let the players know when it's their turn to move. And the bots, as I was saying, was following a variant of the algorithm that I presented in this paper. So we designed 3 maps for this game. And on top, you just see one optimal solution for each of these maps. So we had 24 participants in total, and each participant basically was playing each map only once, with only by themselves and 2 bots, possibly another human player, or all of them are human players. So these plots show the ratio of the average score that they collect as a team over 200 turns to the best possible score. So on this end, we have the score that we obtain where all 3 robots are following the algorithm that I presented. And here we have 4 experiments. 1 player was playing with 2 autonomous robots. And this dashed line is basically just the average, right, for each set of 4 experiments. And what we observed was kind of interesting in the sense that, of course, when something is already giving you near optimal, you expect some performance reduction. But for some of these maps, there was a very well-defined, monotonic, constant reduction in the performance, whereas in this case, the performance was going down when you take the average, but then there was this uptick. So it almost seemed like heterogeneous decision-making was kind of the problem, but when everybody, like all the robots were controlled by one human, they could actually do a bit better than having another autonomous system in the team. So, I mean, I think there's a lot of open questions in that area where we have this learning or optimization problems with uncontrolled decision makers or heterogeneous decision making. Just to summarize, the things that I mentioned in this talk. So coordination in almost all multi-agents is the key. It's the most important thing that determines the overall performance. It is usually difficult to achieve due to various reasons coming from size and operation, like distributed decision-making and control, partial information, and possibly trying to achieve very complex coordination. An important area in this field is actually designing scalable and provably correct algorithms for achieving coordination in long horizon missions. Related areas would be systems and control, optimization, machine learning, and game theory. Today, I just talked about a path trajectory planning problem with using game theoretic tools. And we have some of our preliminary works already published, and some is currently in progress. And I also want to mention that the main body of this talk was again a thesis topic for my master's student, who's a master's student in the electrical and computer engineering department. So with that, I would like to thank you all for your attention, and that's the end of my presentation.
Thank you. So, any questions?
Okay, so maybe let me ask a simple question. Maybe I missed it from the first part of the talk. So you have some kind of temporal information or time windows, and I was trying to figure out are the time windows assigned when the tasks are assigned? So they're kind of fixed up front?
So yes, so each time the task arrives, we assume that the task has some arrival and departure time. So this already comes in as a task specification. So the task specifications are basically location, time window, and something that says how many robots would be needed over that time horizon.
So, but you don't know when the tasks are going to arrive, or do you know?
So the way I presented this was basically in the beginning of episodes, these tasks were given, like we are giving these specifications as a team of robots. We know the arrival and departure times that are going to be happening over the, let's say, next episode, which might be, you know, the operation during the next hour or so. Then they try to solve this. Now, there could be a different version of this, an extension of this, where we wouldn't actually know the arrival times, where the robots would go and possibly during the episode, task arrive dynamically, something shows up somewhere else in the environment, and we expect the robots to respond to that. That wasn't captured in this setting, but I think it could be extended in that direction.
Okay, and one more quick, simple question here. So is it possible that tasks have additional constraints? Like two tasks can arrive at the same time, but one task is to be done before the other task can be done, or if that task is not done. I mean, I'm trying to think how broad you can
that's a very good,
still have the algorithms that work.
Yes, that's a very, very good question. In this presentation, I didn't talk about tasks that had couplings like that. So each task was kind of independent of the other tasks in its completion and only dependent on the number of robots. I think we could couple them. I mean, there's because there is no reason why we cannot couple them actually, because this total score can actually accommodate that. I mean, at the end of the day, what they're doing is there's some global score, which is kind of some of values from the tasks, and they're considering their marginal contribution to the score. Now, with the value functions that I presented here, it doesn't have that coupling, but we could add that coupling where the tasks, you know, value functions also dependent on something about how the robot served some other task, right? So I think the overall structure would still work but we haven't looked at that yet. I think it's a very good question.
Okay, thank you. Yeah, that's
Other questions?
Yeah, I have a couple of questions. The
Mhm.
first one is, how scalable is this technology? The second one, what happens if there are many more solutions to a particular task assignment? And the third is, have you looked at any reinforcement learning techniques to accommodate this kind of scenarios?
Okay, all very good questions. So I'll start with the last one. I think this setup could easily accommodate reinforcement learning, and I think that's a very good point that I'm also interested in, like exploring how reinforcement type of ideas can be applied to these problems. Again, there will be something about, it wouldn't be just an immediate application of reinforcement learning tasks, because again, we have some cooperation between the robots, and there's some sort of who gets the reward and how much of the reward should be assigned to which agent type of questions that comes into the picture. But I think at a higher level, that this problem is definitely a good fit for reinforcement learning type of ideas. We plan to explore it in the future. The other one, scalability. So this, if you see this slide, so this idea with the filtering of actions actually make this algorithm quite scalable. So because when you filter these things, if you don't do any filtering, the action sets basically explodes with the horizon. There is a huge number of things, options that every robot needs to consider. At every time step, everything slows down. Even a single iteration would take possibly, if you were to take these action sets, for instance, a single step might take a minute. But after doing this removal of actions and making them very compact while keeping the global performance unaffected, we can actually make this very scalable. For instance, in this case, with this many robots and this many tasks, it takes in the order of seconds. So of course, in general, of course, we may want to have longer horizon, possibly maybe more robots and tasks. It would still be applicable in real time, in the sense that you would need something in the order of minutes, for instance, to find the solution and dispatch the robots, let's say over the next hour. So another thing is basically, as this thing grows, not everybody is communicating or coordinating with everyone, right? If we increase the size of this space, right? Maybe there are 10 stations, right? Much bigger area. Those things are actually optimizing their trajectories in parallel. So there wouldn't be much scalability concern in that regard either. And your third question was, what was it?
What happens if there are more than one solution to a particular task allocation?
So if there are more than one, we don't really differentiate between them. I mean, they are equally acceptable. So say completing this task first, then completing this task, or maybe going there and preempting this task, going there and coming back. As long as they're all completed, right? As long as I'm maximizing the total value from the task, we don't differentiate between multiple solutions.
Okay, thank you.
Sure.
Other questions? The last call. Thank you very much, Yasin. So thanks everybody